We have just presented the steepest descent and its accelerated version for handling the optimization problem we face. One weakness in these methods is their complete disregard to the fact that our unknown alpha is expected to be sparse. We turn now to present an alternative algorithm called ISTA that is specifically tailored to the structure of our problem. Here is a general and lovely concept in optimization theory that we will be building upon. Suppose that we are given a function to minimize f of alpha, and this task is simply too hard to manage. We define a proxy, a new function q of alpha, parameterized by alpha 0. This function is required to satisfy three conditions. The first is that q of alpha 0 should align with the function f of alpha at alpha 0. The second condition is that q upper bounds the function f everywhere. The third condition is that its slope around alpha 0 should be the same as the one of f of alpha. Armed with this proxy q, here is an interesting claim. Choose an initial alpha 0 and minimize the function q around it. This will lead to alpha 1. Redefine the proxy around alpha 1 and minimize it. Proceed this way and get a series of points alpha k. The claim is that these will necessarily converge to a local minimum of the underlying function f of alpha. Moreover, if the function f is convex, the above process will find its global minimizer. This way, we have replaced one tough optimization problem with a series of them. Therefore, this process makes sense only if the minimization of the q functions is much easier to handle. Also, this entire process relies on our ability to build these proxy functions somehow. Now let's bring the above idea to our problem as posed here. We define the function q in the following way as the original function f plus these two quadratic terms. Observe that the sign in front of the last term is negative. The first thing to do is to verify that the three conditions q must obey are met. The first condition is trivial to check, and it is true. The second condition is true if the quadratic part we added to f is never negative. This will be the case its Hessian is positive definite, which leads to the condition you see here on the parameter c. The third condition regarding the slope around alpha 0 is met as well, since the additional part has a zero slope at alpha 0. So the choice of q we made is valid. The question now is whether this q would be easier to minimize compared to f of alpha. This is the complete expression we have for the proxy function q. And with little bit of algebra, we can show that it is equal to this alternative expression. Observe that the green expression can be computed easily as it involves known ingredients alpha 0, d, h, and z, the given image. If you're wondering what just happened here, notice that the most problematic part in the expression, the squared L2 of h times d times alpha, vanished. And this is due to the choice to subtract the last part in q. We have just seen that q has this form, where now we have defined the green expression from before as v0. Is this minimization easy? Luckily for us, the answer is definite yes. And this must remind you of something we already did. The expression we got can be broken into m separate 1D optimization tasks of the same form, each handling one entry in alpha. These problems are known to have a closed form solution that relies on a soft thresholding, which looks like this. Returning to the task of solving the minimization of q, the solution is given in closed form by computing the vector v0 and then applying a soft thresholding on it with a threshold set to be lambda divided by c. This is quite easy, and applying a chain of such steps is appealing. If you are interested in better understanding the optimality of the soft thresholding for the L1 case, we refer you to the 6th class in Section 4 of the first course. In addition, we present a MATLAB demo next that presents this concept of shrinkage from an empirical point of view. Returning to our deblurring task, we had this minimization to do. We have built an algorithm to get the minimizer by a chain of minimizations of proxy functions. The iterative formula we ended up with is this. Notice how similar it is to the steepest descent. In fact, we apply steepest descent on the quadratic part of f of alpha and then shrink the result to make it sparse, serving the second L1 term by a projection. This algorithm is guaranteed to lead to the globally optimal solution of the original problem. This is the iterative shrinkage thresholding algorithm, also referred to as ISTA. Variations of this method were proposed by Figueiredo and Nowak in 2003 and by Debussy, De Vries, De Mol in 2005. Just like the acceleration for SD, we can propose a similar concept for ISTA, leading to a fast ISTA, or as it is actually called, FISTA. Here is the general idea. This is the regular algorithm which updates alpha somehow. Moving to the accelerated version, we will use the same formula to get a temporary vector decay and then use an acceleration on it just as before. In our case, this would be the update equations to use. This method, termed FISTA, was proposed and analyzed by Beck and Teboul in 2009. In their work, they also suggested formula for the free parameters mu and m. To summarize, we introduced ISTA, relying on the majorization-maximization approach. Alternative techniques to derive the same algorithm are available using the Proxy method. Over the years, various researchers suggested alternative and related methods, such as split-Bregman, ADMM-based, which we presented in the first course, parallel coordinate descent, and more. All these algorithms have one clear thing in common. In every iteration, they multiply by HD and its transpose and perform an element-wise shrinkage of some sort. Before we leave this topic, we want to add one small ingredient to our story. What if the L1 would be replaced by a more general separable expression of this form? Well, as it turns out, we can follow the same path and rephrase the problem to a chain of these tasks, and, not so surprisingly, these have a shrinkage-based one-shot solution. The function rho dictates what kind of curve we get in the shrinkage, but all tend to zero small entries and leave large ones almost intact. The demo we present next show these curves and how they are obtained. We do emphasize, though, that if rho is not convex, then the resulting ISTA will give only a local minimum solution.